peacock mantis shrimp, both beautiful and deadly to other sea creatures that are in its approximate weight class. But what can it see that humans, that you, can't see? And what can we see that it can't see, is the question. The peacock mantis shrimp, they're only a couple inches long. They're beautifully colored and they live in coral reefs, but they're a prolific and excellent hunter. They have a mechanism in their front appendage that they can basically accelerate as fast as a speeding .22 caliber bullet, which means that they can crack shells and they can use it to fight each other and as part of a hunting. But they also have amazing vision that's alien and very different than human vision. To understand how this is so, first you have to understand a couple things about what we can see, what we consider visible as humans. And most people are familiar with the rainbow. This is Roy G. Biv, red, orange, yellow, green, blue, indigo, questionable color there, violet. I think there's a story about how the indigo color was just added just because I think Newton wanted it in there. But anyways, it's recognizable. But this is only part of what's known as the electromagnetic spectrum, which is another name for electromagnetic radiation, is another name for light. It's commonly called light. Now, light can be visible to us, and it can also be visible to instruments where we can record it. So we can have cameras that can see ultraviolet, we have cameras that can see visible light to humans, and we have cameras that can see infrared. And infrared is sometimes called heat. I mean, we experience near infrared as heat, but that's to say, if you go along this spectrum, we're right here, and this very narrow band is what we can see. But we can differentiate very well one color from another within that band. So we can only say, oh yeah, is this yellow? No, we can say this is like just not quite the same yellow as another yellow. And how do we do that? Well, actually, before I get into that, let me explain this spectrum here. On the short wavelength, now wavelength is, you can see here, wavelength going from long to short. I mean, just so it happens that the sky looks like it's the seed floor. That's a coincidence. But what I'm really trying to show here is that on the radio waves on the far end, then microwaves, which are inside of your microwave, that's the kind of light that's used to excite water molecules that then heat up your food. But those wavelengths are actually big enough that a human can, it's like something like that. You could see it. But then as you get towards infrared, they start getting down smaller to grain of sand size, and then smaller and smaller, and then finally you get this visible range here. Wavelength is measured in nanometers, and when you have this range of human vision, it goes from 400 to 700 nanometers. And then if you go shorter than 400, you end up getting ultraviolet, which we can't see, but is certainly being produced by the sun. And the lower you go in wavelength, the higher you go in energy. So ultraviolet light comes all the way from the sun through the atmosphere, and then in a lot of cases penetrates deep into the ocean, much further than other colors. If you think about what we think of the ocean is blue, right? Like dark blue to darker blue, basically. We think it's a muted world of blue shades. But actually, if you can see further into the ultraviolet, it's like having a whole rainbow extended. So the mantis shrimp can see what's visible to humans, although they lack the ability to finely distinguish certain colors, but they also can see ultraviolet light. Now, once you get a really short wavelength, you start getting X-rays and then eventually gamma rays, which are special kinds of high energy X-rays. And those, it's like the wavelength is so short. I mean, nanometers are short, but not it no longer behaves the way that we imagine light. Like you could see an image, or it could make a shadow or something like that. Once you're in X-rays and gamma rays, I mean, I guess an X-ray does make a shadow in the sense you get an X-ray at the doctor's. We actually have to beam X-rays at you. It does make a shadow. That shadow, you can see your bones, more clearly in it. So yeah, okay, there's a shadow, but it's not quite what we imagine. So once you start getting into microwaves and X-rays and beyond in either direction, we don't really understand that to be an image. Now, the mantis shrimp, they have a totally different system than us. We humans have 3 color receptors called cones that are in the human eye, and the signal is integrated in our brain, and we perceive it as this world of color and rainbows. But the sensitivity that we experience is actually here again 400 to 700 nanometers. That's the rainbow that we think of. But our sensitivity has 3 peaks to it: blue, green, and red. And now look, side note, this overlap between green and red here, and some people that those signals get crossed, and that results in red-green color blindness. Okay, but that's beside the point. Now, this light, electromagnetic radiation, that's visible to us because we have these 3 light color receptors, and that's what they're detecting. They're detecting just these things. And when you sum them up, you get this whole continuous thing. It's like when the monitors originally had, 16-bit, 32-bit. Now they have millions of colors, and really it's like we can almost see millions of different colors. So, but this guy can also see something that we can't see. First of all, they have compound eyes. And the eyes can look at different things from each other. They can look independently at different things, and they can see depth with just one eye. We have 2 eyes that gives us the ability to see really well depth. If you had an eye patch, you might get hit in the face with a baseball. Like, it's as simple. I'm sorry, but these guys, since they have so many different functions to their eye, they can actually, one of them is that they can perceive depth with just one eye and look at 2 different things with their eyes. But besides having the approximately 3 that we have, they have as many, some literature says as many as 16 light color receptors in their eyes. And they extend from what we can see, but they also go into the ultraviolet, and they're arranged in regions, bands, 6 bands of detectors, and each band has several different capabilities. So the most crazy thing is that we can't even understand the final thing, which is they can also see polarized light. Maybe you've heard about polarized light because that's a feature you can get in a nicer pair of sunglasses. you can use this polarized light to help reduce the glare on the top of the ocean, as if you're in a boat or on driving on the highway, where you have the sun coming in and hitting the flat surface of either the road or the surface of the water, can tend to line up and align light. What does that mean? Well, if you look here, this is a light wave, a single beam light wave, and it's coming from back here somewhere, and it's traveling in this direction. You might be wondering, well, it kind of looks like a wave, but it looks like a double wave actually, and you'd be right. So again, electromagnetic radiation. What does that mean? That means that you're having variable electric and magnetic fields that are at right angles to each other, forming a plus pattern where you have your electric field oscillating this way and you have your magnetic field oscillating this way. And when you have just the light coming out of just a source, a single source like the sun, so far away, light is coming pretty much from there, but it's also could be any orientation. And so polarization has to do with the orientation of light. So when you have light that comes from the source, and these waves, these double wave, the variation, the oscillation in electric and magnetic fields, that's periodic and like sinusoidal, which means it's like the wave, it's just like a rolling wave that's always the same. Now, this is coming in. If you have a vertical slit, then this electric wave can be blocked out. So we have, if you have a slit of a certain size, that can produce a polarization effect. That's how it works in sunglasses. So, but okay, that's called linear polarization because it would be a linear slit. But like I said, this is a double wave, and if it's coming at you like this, ooh, it's hard to do. It's like patting your head and whatever. But if you have this axis here, which is the travel direction, if you now rotate along that axis, see this green spiral here to represent that. Now you have this sort of cross pattern, plus symbol pattern of the crossed waves, but you don't know this orientation, so it could be rotating around. So okay, so that's circular polarization. Now, guess what? The peacock mantis shrimp can see both of those kinds of polarization, and depending on how you think about it, they can see, I think they can see diagonal polarization too, but that's really just linear on an angle. But what for? I mean, we can't see it. We're doing all right with our vision. Well, like, they're also beautifully colored. So you have a couple things that could be for mating, attracting a mate, or repelling an adversary. Maybe it helps them be such dominant hunters, and maybe we can't really know. I wish we could know, but maybe they use it for communication. Now, what I saw, a theory that I liked what I saw, is that since they can see polarization, a team a couple years ago measured the polarization at different parts of the Earth and different times of the year underwater. It's not just horizontal polarization from the surface that you might get, but also you're somehow getting effects from inside the water. So what does that mean? It might mean that the mantis shrimp can use polarization to navigate, to make a mental map of an area and to know. I mean, they say some animals have the ability to detect magnetic fields, but I mean, if you can use polarized light, maybe you can navigate, But then also, maybe it helps in an advantage with hunting where there's the light coming behind in certain circumstances. Something goes in front of the sun. Who knows? Who knows? I mean, can only imagine. So, in conclusion, that's what I think he can see, or we think. And also another question that boggles the mind is, how did they test this? Well, I think in one case they shine slightly different color lights at them and had them attack different kinds of food, behavioral science, I don't know. We'd have to get into it more another time. But they can really see a lot, but don't feel too bad, because what they have increased polarization vision and vertical, horizontal, circular polarization, and maybe as many as 16 different color receptor cells. They have compound eyes. Their eyes can look in different directions, and one eye can focus where both of us. But don't feel bad, because they can only tell the difference between like yellow and orange. So think about that. And please like and subscribe, and check out mindofitsowndesign.com for projects, prototypes, and process design. Thank you.